Have you ever really thought about how a battery works or, how electricity can actually flow through a liquid? Well, that's the world of electrochemistry, and today we're going to tackle a really core concept, how we measure and understand the conductance of solutions. So, let's jump right in.
Okay, so here's our game plan for today. First, we're going to start with the absolute basics, the fundamental properties that govern electrical flow. Then, we'll kind of move into the lab to see how we actually measure this stuff. After that, we'll get into a really key idea called molar conductivity, see how concentration messes with it, and then we'll put it all together and solve some actual problems.
All right, first things first, let's lay down the foundation. To really get a grip on conductance, there are 4 key electrical properties you absolutely have to know. Think of them as the building blocks for everything else we're going to talk about today. We've got resistance, conductance, resistivity, and conductivity.
So let's start with a term you've probably heard before, resistance. We use the symbol R for it. A great way to think about it is like, electrical friction. It's basically a measure of how much a material fights back or opposes the flow of an electrical current, and we measure this in ohms.
Okay, so how do we actually calculate it? This formula right here tells us everything we need to know. Just imagine electricity trying to get through a hallway, right? A super long hallway. That's L, means it's a longer journey, so there's going to be more resistance. But a really wide hallway, a larger area, A, makes it way easier for everything to flow through, so less resistance. It's exactly why a long, skinny wire has way more resistance than a short, thick one.
So we've got the physical dimensions down, length and area. But what about the material itself? That's a huge factor, right? And that's where this Greek letter rho comes in. This is called resistivity, and it's a fundamental property of the substance. I mean, think about it. You could have a piece of copper and a piece of rubber that are the exact same size and shape, but their rho values, their intrinsic resistivity, are completely different. That's why one conducts electricity and the other, it doesn't.
Okay, so if resistance is all about opposition, then conductance is, you guessed it, the exact opposite. We use the letter G for this one, and it just measures how easily current flows through something. It's literally the inverse of resistance, and we measure it in a unit called Siemens, or S. And the relationship here is really straightforward. Since G is just 1 over R, we can basically just flip our whole resistance formula upside down. Now, when we do that, the inverse of resistivity, that's 1 over rho, gives us a brand new property. It's called conductivity, and we use the Greek letter kappa for it.
So, just to be super clear, kappa, which is conductivity, is simply the inverse of resistivity. It's the real measure of a material's built-in inherent ability to conduct electricity. And for what we're doing today, understanding the conductivity of a solution, that's the ultimate goal.
Okay, so we've got our definitions down pat. But, theory is one thing, and practice is a whole different beast. How do we actually measure this stuff in a liquid? It's not like you can just clip an ohm meter onto a beaker of salt water and call it a day, right?
So, measuring the resistance of an ionic solution throws a couple of unique curveballs at us, things we just don't have to worry about with a solid wire. And we've got to figure out how to solve these problems before we can get any kind of accurate reading.
Okay, problem number 1. If we try to use a direct current, a DC source like a regular battery, it actually starts a chemical reaction in the solution. That's electrolysis. And that means the solution is changing while we're trying to measure it. Not good. So the fix? We use an alternating current, or AC, which just flips back and forth really fast and prevents any of that chemical funny business. Now, problem number 2 is more of a physical one. How in the world do you connect a liquid to a circuit? The answer to that is a very clever, specially designed device called a conductivity cell.
And here's what one looks like. If you take a look at a typical conductivity cell, you'll see 2 really important things. First, there are these 2 platinum electrodes. They're often coated with platinum black just to get the most surface area possible. But what's even more important is that they are held at a perfectly fixed distance, RL, from each other, and they have a fixed area, RA. This fixed geometry, it's the key to making this whole thing work.
So think about it. Since that distance L and the area A are physically built into the cell and don't change, their ratio, L divided by A, is also going to be a constant. And we give this a special name, the cell constant. We write it as G star. This number is unique to each individual cell, and it is absolutely essential for all of our calculations. So, to recap, we have our AC power source to avoid chemical reactions, and we have our conductivity cell, which we filled with our solution. The next step is to place this cell into a very specific type of circuit called a Wheatstone bridge. In this diagram, our cell is R2, the unknown resistance we're trying to find. It's a really clever setup that lets us figure out that resistance with incredible precision.
The real genius of the Wheatstone bridge is all about finding balance. What we do is adjust R1, which is a resistor we can change, until the detector right there in the middle reads 0 current. We call this the null point. When that happens, it means the bridge is perfectly balanced. And at that exact moment, we can use this super simple formula to calculate the unknown resistance of our solution, R2. It's really elegant.
Okay, so now we have a solid, reliable way to measure the resistance, which means we can also figure out the conductivity of a solution. But this leads to a new question. How can we fairly compare the conductivity of completely different substances? I mean, how do you compare, say, hydrochloric acid to acetic acid in a meaningful way?
The answer to that problem is molar conductivity. We use the symbol lambda m for it. What this does is it standardizes our measurement. It basically asks the question, what is the conductivity we get from dissolving exactly 1 mole of a substance? By doing this, we can now directly compare the conducting power of 1 mole of hydrochloric acid to 1 mole of acetic acid. It finally gives us a true apples-to-apples comparison.
And the formula to calculate it? Super straightforward. Molar conductivity, or lambda m, is just equal to the specific conductivity, kappa, which, remember, we now know how to measure, and we just divide that by the molar concentration, C, of the solution. That's it.
Now, one of the biggest things that affects conductivity is, of course, concentration. So let's take a look at what happens when we change the concentration of our solution, basically by diluting it. We'll see how that affects its molar conductivity. And what's really cool is how this reveals a huge fundamental difference between two types of electrolytes.
Okay, now this is a really crucial distinction, so pay close attention. For a strong electrolyte, something like potassium chloride, it's already 100% broken apart into ions in the solution. So when you dilute it, you're just moving those ions further apart. This leads to a small, steady, pretty linear increase in molar conductivity. But for a weak electrolyte like acetic acid, which only partially breaks apart, dilution is a total game changer. Adding more water actually forces more and more of the acid molecules to dissociate into ions, and this causes a massive, sharp, dramatic spike in molar conductivity, especially at very low concentrations. They behave completely differently.
All right, we've gone through a ton of theory. So now, let's get to what might be the most important part, especially for your exams, actually taking these concepts and formulas and using them to solve some problems. This is where the rubber meets the road, where we really test our understanding.
Let's walk through this first example together, step by step. So the problem gives us the resistance and the conductivity of a solution, and it's asking for the cell constant. Step 1, as always, is just to list out the data you're given. Don't skip this. Step 2, figure out which formula you need. Well, we know that the cell constant, G star, is just resistance times conductivity, R times kappa. Easy enough. Step 3, we plug in the numbers. And finally, step 4, we just do the calculations to get our final answer.
Okay, before we wrap up, let's do a super quick recap of the most important formulas from today. We've got our basic definitions for resistance and conductance, we've got the cell constant, G star, and the 2 ways to think about it, and of course our formula for molar conductivity. I would definitely make sure these are front and center in your notes because you're absolutely going to need them.
And that's a wrap on Part 1, all about conductance. In our next explainer, we're going to take all these principles and use them to dive into the really fascinating world of electrochemical cells, which you probably just call batteries. We'll look at how they manage to convert chemical energy into electrical energy, and we'll introduce the very famous, very important Nernst equation. See you then.